All right, then, Andrew, do you quickly want to introduce yourself before we start?
Sure. Yeah, I'm a fourth year PhD student at University of Oxford, supervised by Arnaud Doucet and Tom Rainforth. Yeah, so I guess what I worked on is like diffusion models on like data types that are not standard, so like discrete data types or trans-dimensional data, like dimensions that data that changes dimensions, like multimodal data as well. So a lot of what I've done is making like diffusion processes for that kind of non-standard data. Yeah, like so one of the most recent things that I've done with Jason here at MIT is this like discrete flow models idea, trying to translate flow matching to discrete data. And then this paper here like builds on that work a lot and yeah, kind of solidifies the connections to the flow matching in continuous spaces. So I guess we can, yeah, talk about that now.
Yeah, and to do that, I would maybe first look at their notation or their setup. So maybe to like we'll be using this guy here a bunch, and this guy is just down here we write our thing, and whenever the input is the same as the thing, then this guy is 1, and otherwise it's 0. And then more in terms of notation, I guess we can maybe assume that we all know what like the general flow matching setup, right? We have some prior distribution. Do they actually write? Yeah. Here's some distribution over x zeros and some distribution over x ones. So if we just want to generate data, then this is like a prior and a target distribution, right? And correct me if I say.
Yeah, it's all good. Makes sense.
Yeah, but then sort of we can have this stuff being sampled not independently here, like with some pi, where we have a coupling between x0 and x1. But I guess for most of what we'll be talking about, it's just that we sample them independently, so something from our prior and something from the target. So is this right? This is fine to
yeah, like pretty much all the way through they use like the independent one, except for like when they do some conditioning task. I think their like source distribution or the prior distribution becomes like some tokens from the clean data and then the rest of them being
okay.
mixed.
So it's then kind of like in the data dependent couplings paper, or do they do you know this flow matching with data dependent couplings thing?
Yeah, I'm not familiar enough to like know if it's the same thing or not. But yeah, it's just like they're starting the process like halfway through the corruption. Like you only mask some of it, and then because you haven't fully corrupted all the data, then it's kind of like your prior distribution is coupled.
Yeah. Okay. And to the 80 friends of the sun, if you have any questions, you can ask them in the chat, or you can just unmute yourselves. That also works. And if Itai Gat or any of the other authors is here, then please make yourself known, and we know that we can rely on your help. But Andrew, is there anything else about the notation part that we should take care of here? Like maybe
Yeah, I
is there
think one of the
anything
important ones is like the notation that xi bar is x or all the dimensions of x except the ith dimension, because
uh,
that comes up a lot where you need to like make sure all the dimensions except for the ith dimension are the same, and then the ith dimension is something that varies.
Okay, so we have always like right, we have our sequence of positions or our sequence of random variables, and with the superscript we indicate the position, and if we have the superscript with a bar, like our xi is only a single position, but the superscript with the bar, so the xi bar is a sequence again, but now the sequence length is n minus 1 and it's missing the xi.
Yeah.
Okay. Yeah, then I guess this notation stuff here is done. And what do you think here? Do we need to say something here?
Yeah, I mean that's just the example of the like non-independent coupling where some
Yeah.
of the x0 dimensions are like equal to the x1 dimensions.
Why is that interesting?
It's for like the conditional text generation. Like they'll condition on some
Okay.
clean data.
So if I already have a prompt, for example, at the beginning of my sequence, then this would fall under this scenario where
Yeah.
now we're in our prior, we have a or yeah, we have a prior that is a distribution conditioned on the target distribution.
Yeah. I guess the joint is like data p of x1 and then p of x0 given x1, where it's
Yeah.
just masks out some of it.
Okay. Then probability paths. I mean, no, I guess we're talking about discrete flow matching, right? So we can also spend some time on flow matching, I would say. What do you want to say here?
So yeah, I guess it's the same idea as continuous flow matching where you have like x0 and x1, and then xt is some amount of x1 plus some amount of x0, like the linear interpolation. And then how that you translate it is you have this distribution p of xt given x0 and x1, and then you just set it to be like a delta function on some amount, like some probability of like being equal to x0 and some probability of being x1. Also, so like in the continuous case, it would be like the delta function as like a linear interpolation between x0 and x1. But here, I think in the simplest case, it's like, kappa times delta x is equal to x0 plus 1 minus kappa delta xt is equal to x1. So it's just like,
Before we get into this guy, so up here, I guess we're just writing out that we can marginalize over our over like the prior. Or I guess if this is an independent coupling. And then we have this kappa and these W's going on here, which we maybe want to talk about for this for this discrete case, which we maybe haven't seen in the continuous case. But now I think CKJ is making the nice point of why do you want to do discrete flow matching and not just do the stuff autoregressively?
Yeah. I mean, I think someone in the chat said it is like with autoregressive, you're like you have to have like n forward passes of your transformer to do a sequence of length n. But if you do say like diffusion, then you should be able to like denoise everything in parallel, and then maybe that could be faster. And also, if you're denoising in parallel, then you get like information being transferred not just in this like left to right fashion, but being able to like make some decorruption over here and then some decorruption over here, and then being able to like denoise everything in, jointly, so that all aspects of the sequence can influence like the generation.
And nice that the CKJ also identifies themselves as Chaitanya. Thank you for the nice question. But then Andrew, you now say, right, you said two things, maybe this bidirectionality and the speed. So maybe let me contest the speed one first, right? If we also want something good, and if we can also sample a sequence in one forward pass, right? We could model each position of a sequence independently, and yeah, have this approximation of everything, every position being independent. And then what we get would for sure be garbage. Like if position I doesn't depend on position J. And now for everything that you predict at once, right? Stuff would need to be like if you predict 6 tokens together at once, then these predictions would need to be independent of each other.
Mm-hmm.
Like if you predict probabilities for 6 positions at once, and then you decode those probabilities to concrete tokens, then this decoding step makes the positions that you get independent of each other.
Yeah.
And now, so this means that if we have this, let's say it discrete space flow matching, or discrete flow matching approach, where so something that's not like Dirichlet flow matching, for example, where we have like relaxed stuff into a continuous space on the simplex or so, then if we have fewer steps, so we have a sequence of length n, right, or n length sequence, and if we have fewer denoising steps than n, then doesn't this automatically mean that we will incur some sort of degradation, because at some point we will have to, or we need to take at least 2 positions and predict probabilities for them and decode them independently.
Yeah, I guess it's like if there are positions that have a strong correlation with each other, or they're both like very deterministic given the current set of information, then you're allowed to decode them both at the same time without incurring any error. Like if the current amount of information revealed is enough to like make the rest of it deterministic, then infilling everything in one step, even if each point is independent, because each one is a delta function conditioned on the current amount of information, then you're not incurring any error. So it's like being able to do it in parallel, you can exploit if there are these strong conditionings given some amount of information in the data. If such a thing exists in the data set, then if you decode in parallel, then it can exploit that.
Okay, then a very good example for what you're saying would maybe not be language so much. Let's say maybe for language, I don't know, okay? But let's say maybe for language, just 20% of positions that are very strongly correlated. And if you have one, then you have the other. So if you have like a sentence, I guess,
Well, I guess it's like if you have like take any sentence and you corrupt just a few amount of the characters, but like each word is still uniquely identifiable if you like assume they're from a dictionary, then you should be able to infill every one of those words if you like assume everything is spelled correctly.
Yeah, but I'm just now trying to make it concrete. What you're saying is our sentence is the woman jumped over the fence and she succeeded. And then we have the word woman. Oh, am I no? Okay. Anyway, we have the word woman and she. And if everything else is given, then the word woman maybe makes the word she clear. But if it's it could also be man, and then it would be he. And here is like a situation where then predicting we might have 50-50 probability for the word he and 50-50 probability for the word woman, and then decoding them both at the same time. Like we predict those probabilities and then we decode them both at the same time. Then we might end up with the man jumped over the fence and she succeeded. And we would end up with something bad. Is that a good example?
Yeah, that's the failure case. Yeah.
That's a failure case, and the opposite if it's clear, or if it doesn't matter which one of both you choose, right?
Yeah, say like woman and she has already appeared in the sentence, then like the other locations of woman and she could be like just put in directly.
Yeah.
Condition
Okay.
and stuff.
But then Chaitanya is making an example where probably we have many more cases in biology where like we have positions that are independent of each other. Like if we have some regulatory DNA, then like for some positions it basically doesn't matter what you put there. You could put anything there. So it is like completely independent of anything else, and like just some irrelevant positions, and decoding them all at once would certainly give you some speed ups. But then I think for this sort of stuff, it's actually kind of interesting to look at some predictors that can tell you how much uncertainty is left where in the sequence. But anyway, I think this is getting too far from motivation of why flow matching. Uh, in general, I think the speed motivation is kind of weak, and your other motivation of bidirectionality is a little bit stronger. And I think there's a third relevant motivation, which is controllability and more flexible conditioning. But right, your other point is if we decode autoregressively and we don't have and we have like a fixed decoding order, then only past tokens can inform future tokens. But of course, there are like any order autoregressive models, right? Where we model or where we train with any ordering of the sequence, and then we can decode with any ordering of the sequence. And I guess some people, or you can sort of put this training also into the framework of a diffusion model. Or you can talk about this as a diffusion model, right? You have your whole sequence and you randomly corrupt some positions, and then you have this or you have the whole sequence with like a few positions corrupted, and you predict the clean sequence from it. And then during inference, you at the beginning just have a fully corrupted sequence, predict all the clean positions from it, and then you decode a random fixed a random position, and then you keep that position fixed, and so on, and you continue. Those are actually were also some of the very similar to some of the first discrete diffusion approaches. But now the third one, controllability, I would say is also very important, because if we have language, right, then how we prompt it is very oftentimes like this forward in time. You have a question and then the answer comes afterward. You have a whatever, like some description and then the answer comes afterward. But if we have some biological tasks, then maybe the sort of conditioning that we want to do is different. And we have some parts that are filled in, some other parts that aren't filled in. And maybe we have some yeah, like some other type of conditioning that can't be described in a prompt, or that can't be described by already having a part of the sequence given. And like, yeah, we want to incorporate that conditioning everywhere in sequence, and make sure that we or I guess diffusion models just are a little more controllable. Of course, with your framework, on this framework here, it's not clear to me yet how to do guidance, and maybe we can talk about that a little bit more later on as well. But then would you say that's sufficient motivation?
Yeah, I mean, yeah, it's good enough for me.
Okay, let's see if it's also good enough for Chaitanya. And for the next question, Chaitanya, we're very happy to see them in the chat. We're even happier if you unmute yourself and talk with us. But then let's look at yeah, we wanted to. I want to ask you what's okay, maybe we've done some flow matching, right? And this guy is pretty clear to us. We have this probability path, which we have our sequence, and then we have our time 0, our time 1, and then we have some t in between, like this t going between 0 and 1. And then this gives us a probability over the x. This gives a probability over the x at this time t, this probability path thingy here. And we also have these conditional probability paths where it's conditioned on a sample from the start and a sample from the end. And then this probability path you can maybe see as a sort of interpolation that you can sample from. And we use this, like we can sample somewhere in the middle from, and we use this during for training, right? And then in the end, after training, we end up with a vector field that can also trace out this probability path when we start from an x0, just because similar to what we see in diffusion models with this marginalization. But yeah, maybe we've seen all of this. But now we look at this guy here, and we have these kappas, so many subscripts, superscripts, first of all, right? We remember what this superscript does. It tells us which position in the sequence we're talking about. And now, what is the W? Right, we want to define our conditional probability path. So I give you an x0, I give you an x1, like prior sequence, end sequence, and you're supposed to give me the probability for each possible token in our vocabulary for position I. So how do you do that? What do the kappas and the W's mean?
I mean, I think it's clear to look at like, say, equation 9, where you see like the simple form for the interpolation, where it's the W's would just correspond to like a delta function either on x0 or x1, and then your like probability path is kind of like a delta function on one side, and then it slowly like morphs into a delta function on the other side. So it has like starts with like a high probability of being equal to the prior sample, and then moves to a high probability of being the data sample. And then the reason I think they've introduced the fact that you can have more than two, so you have like up to m lots of W, is that you can introduce like more like noise or like more probability in the middle. So like I guess in equation 10 they have PU, which I think is just some like uniform noise, so that rather than always having to be either the x0 or the x1, it could also be just some like random other token. So it's like it could start at x0 and then go to some random other token, but then at time 1 it goes back to x1. So it's still matching the fact that it would start at the prior and end of the data, but it might, you know, take a curvier path through like the discrete state space.
Okay, I agree. And to do the stuff, let me just try to visualize what you just said. So can this guy please get bigger? Aha. We have our pen over here. And by the way, Andrew, feel free to take out your Zoom pen as well, right? You have this, if you go to annotate, you can draw with us as well.
Okay.
But maybe it's better if you just, for now, can correct me where I'm wrong, right? We have this x1 here, and we have this, sorry, we have the ith position of our x0 here, and the ith position of our x1. And the guy is a bit fat, so let me make him smaller. And now we're saying that let's say we have this one or this probability vector, and this is the ith position here. Schwupp. This is our x1, our x0, and this is the ith position. And now in this this fixed, or this it will probably be a one hot vector, and this is just a one, right? If we're sampling from our prior and our training data. And then the ith position in our, oh shit, no, I'm confusing things here, right? So we have our whole sequence here, which is our x0, and this is the ith position, but it's a one hot vector. And in the x1 we also have the whole sequence here, and we have the ith position, and it's a one hot vector, where maybe this guy here is 1. And now we interpolate between these two vectors. Is that right?
Yeah, so I guess if you interpret the vector in each position as like the probability distribution in that dimension, then it starts with like full probability, like 1 on this the x0 value, and then it's like the vector just stops being 1 hot, and it's got like 0.5 on one of them and 0.5 on the other, and then it becomes like 1 hot on the x1 value on the other side.
So here in the middle, we will have something that looks like You said 0.5, but maybe 1/2 is easier. So 1/2 for this position. And so right, this guy in the beginning had 0 for
Yeah.
the ith position. And for this other, and then in the middle, it will be 1/2 here. But now you're saying we have these additional kappas. These kappas, they have their superscript. Like this superscript now isn't the position, but it's the like the intermediate or the additional probability distribution that we use to interpolate to. And this can make it so that in the middle, it's then more spread out, like uniformly. We have some uncertainty everywhere,
Yeah,
and that's
like some
nice,
small
right?
probability in each dimension or something like that.
Yeah. That's kind of nice. Like if we draw our simplex here, then we can also imagine our sequence or our position to be at the beginning here and at the end here. And then if you only have this number 9, this linear interpolation here, then you would only go along this edge. During training your conditional probability path, you would only ever see this edge here, right? Meanwhile, if we have this uniform bias here in the middle, then you also like you spread out across the whole simplex and you go into these areas during training. And
Yeah.
you
Although it, like you have to keep in mind that you don't see the vectors from the simplex. You only see like each one or like each vector is collapsed down into a specific token value. So like even though you're on like the edge of the simplex, you don't actually kind of know you're on the edge because you're collapsed onto like a specific token value.
Yeah, you always like, right, we sample these probability vectors. No, we get these probability vectors via this interpolation, but then we do our sampling and the x1 or the x's that we sample there, and then again the discrete tokens, and they're just one thing. And in this case, it could only be either this corner or that corner. Okay, so it's kind of nice to have this, and I can very well imagine this being important. And maybe that's also an important distinction from your discrete flow matching stuff, that if I think at some point they say that if we have this interpolation, then all of their, or this probability path, then all of their stuff is the same as in your paper. Or maybe this is a over generalization, is the same, but if we include these additional stuff and things, then some of the design options that they point out, they become relevant. What do you say about that?
I mean, I guess in our paper it was like instead of just doing the p of xt given x0 x1, we just marginalize out x0, so we don't think about the possible coupling. We just assume that x0 and x1 are independent, and then if you just marginalize out x0 in either equation 9 or equation 10, then you get like the possible kind of designs that you would use for a p of xt given x1. So you could like roll that like extra noise into just a different form for p of xt given x1.
Did you try any of that, like including additional noise?
I'm just trying to think if uniform interpolation would
Right.
have a form of equation 10. It might do if you have a certain prior distribution, but if the prior distribution is uniform anyway, then you can get the uniform interpolant from equation 9 as well. So yeah, we didn't play that much with the specific form of p of xt given x1.
Okay, but then I think we have a pretty good notion of what these kappas do, and like how we can have these different conditionals that we interpolate between, right? We have this, but the constraint on these conditionals is that it's an interpolation between, sorry, the constraints on the kappas is that it's an interpolation between these. And maybe we can ignore the J for now, like this, no. We can ignore the I for now, like the sequence position, and for the kappas, and just say the kappas are the same across sequence positions. And right here, the numbers, the superscripts, they just tell us the how many W we are using. Okay, then, but let's maybe continue a little bit so we go a bit faster. So, what's this guy?
Yeah, so that's the ODE for continuous space flow matching. So like the ODE update. If you have like small time step h, then your xt plus h is xt plus
Yeah,
h
so
velocity vector.
H is like a little time delta. This is the like some vector field, and we just have an ODE solver, or Euler solver of this ODE.
Yeah.
But now what we actually care about here is this thing here, and then we have this CTMC, continuous time discrete Markov chain, and yeah, I guess the formulation that you told everyone to use, and now everyone is using it, so that's nice. And but here, yeah, let's look at it, right? So we have this sequence here, and it's always a discrete object. It always has like, it's always a one hot vector for every position. Oh no, this thing here literally, right? Because we're only looking at a single position. And now I guess it also comes in that we're sampling all these positions independently in every update step, or in every update, the positions are sampled from each other independently. So this guy here literally is a one hot vector, no?
It's a token value, like it's just a single number or letter or something.
Yeah, okay. So it's a letter, and you could represent it also as a one hot vector.
Yeah, it could be represented as a one hot vector.
And now we take our neural network here, this U, it takes as input the whole sequence, so not just the ith position, right? See, there's no superscript here, but then it predicts for this single position, it predicts something. Well, it predicts a probability vector, and we multiply this probability vector with some little time delta, and we added to some other probability. Let's get to that in a second. And then we sample from this probability vector. There's something fishy going on here. So what's happening? We have this delta here, right? It is 1 if we put in xit. So if it stays the same, so the probability of the thing staying the same is 1. Yeah, okay, so it's not actually 1, right? It can't be the vector that we sample from. But this thing here is also a one hot vector, more or less. We can represent it as a one hot vector. And then we add to this one hot vector the probability vector that our neural network spat out, the U spat out, and we multiply it with the little time delta. So now we have the one hot vector plus the vector of probabilities that also normalizes to 1. And I guess this thing here tells us that we only sample proportional to this, and this guy is normalized.
So the U is not actually a probability vector. It's it can be negative. And it, like, U itself doesn't have to normalize to 1. So like, yeah, you have the delta giving you the one hot, and then in all the positions that the one hot is 0, then the U is positive. And then you multiply it by this small h so that it's like
Very
quite a small number. And then on the 1 position, the U is negative.
negative.
And the negative is such that it's the like negative of the sum of all the other parts of U, so that the whole thing added together is a normalized probability
Okay,
distribution.
very nice, very good. So the U has to be parallel to the simplex, is what Ian Dunn writes. So parallel to the simplex, it is on the simplex, right? It's no. It's parallel to the simplex. It adds up to 0. It doesn't add up to 1. And then in other words, it has a negative number for the token that xi corresponds to at time t, and positive numbers for the other stuff. And the negative number is the same as the sum of all the positive numbers. Okie dokie. Thank you for correcting this. And now, anything we want to talk about here?
Yeah, that's just the like the conditions on U such that equation 12 is a normalized probability distribution. So like, yeah, the like the self connection, the one that corresponds to the 1 in the delta, has to be negative, and it has to be the negative of the sum of all the other parts.
Yeah, okay. I guess we explained that. And here, yeah, maybe we should have looked at this first, but I suppose we all kind of got that, right? This now explains how we sample. We start with a random sequence. Yeah, random sequence, X sample from our prior. And then we throw it into our neural network, the U, and we get out this vector, which sums up to 0. And also, Andrew, will this now always be the case? Oh yeah, now I guess it always must be the case. What our neural network spits out now are always vectors that sum up to 0.
Yeah, you just you output like, you know, maybe all the off diagonal values, and you set the diagonal ones to be the negative of the rows. So yeah, it's always summing to 0.
Okay. And then we have this update rule. Fine. And then we need to, yeah, what do we need to talk about next? I guess this is just standard flow matching stuff, and let's maybe not talk about it. Do you think we need to talk about the continuity equation to like have this, like maybe then we can talk about the continuity equation and look at this figure? Do you think we should do that?
I'm just trying to think if it's necessary to understand the other part.
Then if not, right, then I think we should do the other parts first, the essential stuff first, and then get back to the figure and
Sure.
this interpretation. Because right, sort of what they want to do here is they always show you in this paper, oh, this is what you know from continuous flow matching. Here is the discrete analog to it. And then yeah, that's why they also talk about the divergence here, for example, and the continuity equation. Now we have in the question, could you clarify what Z is? So where do we have a Z? Here we have a Z.
Yeah, Z is just like a placeholder for another token value. So it's like in equation 12 you have a dot to represent like all the values in that vector, and then the Z is just like indexing one of those values.
Okay. But then let's talk about I guess we want to go here.
Yeah, so I guess the thing now is to like you have this probability path, x0 and x1 conditional probability path, and you have Euler sampling with this like U vector, and then you have to try and find the U that would sample according to your probability path that you defined.
Yeah.
And that's what theorem 3 is.
Okay, so you defined our probability path. And now you're telling us in theorem 3, we're looking at some conditional, or we're trying to find the conditional vector field the u that corresponds to the p that you defined in the beginning.
Yeah.
Yeah. Can you explain a little bit what's going on here, or why this theorem is relevant for that?
So I guess when I mean like where the continuity equation comes in is like that's how you're trying to relate these like probability vectors to probability distributions by doing this accounting of like mass flowing in versus mass flowing out, and that gives you like rates of change of your probability distribution. So then what you're trying to do is once you have this like continuity, you have the probability path because you defined that, and then you're trying to find this u, right? Yeah, sorry.
Okay, so we have this or the continuity equation is this shit here. Yeah, basically just this thing here. And we have our probability path, which we now defined. And we need to find the vector field, right? The vector field is also the second thing. Like in this equation, there are two things, the vector field and the probability path. And now we define the probability path. And yeah, we just have to have this equation, and we need to solve it for the ut. And now these folks here give us a discrete version of the continuity equation. And maybe it's better to just look at the intuition that in continuous space, or here's the continuous space drawing, I guess. You look at a little area with the continuity equation. You look at how much you look at what is the density in this area at time t. Then you look at how much flows into the little area, how much flows out of the little area, and that then tells you how the density at this location needs to change at time t by looking at how much flows in and how much flows out. And now we just do the same thing in discrete space, right? And in discrete space, we again have, right, what we have given is for our conditional probability path, what we have given is the probability at a certain time, and we know the derivative with respect to time. So we know how the density here changes at a given time. And now this then, from that, we are able to calculate at this time how much is flowing in from each direction and how much is flowing out in each direction. And that's then how we get this continuity. That's how we get the vector field. And where they do this is here. So yeah, can you explain a little bit how we do it?
Yeah, I mean, I guess it's pretty hard to get intuition from this theorem. Like it's quite
Okay.
difficult to find the u that matches the conditional probability path. And you kind of have to like guess a solution and then check that it by putting it into the continuity equation.
So let's do this. Can you tell us the solution?
I mean, this is one solution. So like the kind of style that both this paper and the solution that we provided before is that you have to like look at the rates of change of the conditional probability path. So that's why in the AT coefficient they have these time derivatives of the kappas. So that's like taking into account that if this probability mass is changing, then the velocity needs to be like sending mass that way, or if the probability is decreasing, then the velocity needs to be like taking mass away. So it needs to somehow look at the time derivatives of the kappas, and then they have this like L, which is like an arg minimum of the kappa time derivatives. And that kind of style of kind of operation also appears in the solution that we provided, where we have this like you're looking at differences in these rates of change of the probability vector, and then you have to only provide probability mass or only provide like flow in directions where one state is losing mass and another state is gaining mass. So it's like you always want the velocity flow to be kind of taking mass away from states that losing it and giving it towards ones that need it. So in our case, it was like the form of a ReLU. So if it was ever negative, then you don't have any mass going in that direction. And if it's positive, then allow mass to flow.
Yeah.
And I think their arg minimum here is doing a similar thing where you have like some baseline amount of mass flow, and as long as you're like more than this, more than that kind of amount of flow, then you're like allow the velocity to be non-zero. But yeah, it's a bit hard to be like specific where the coefficients come from.
Then let's specific about what we end up with. So yeah, what should, for understanding how we train the guy, and for understanding what's the conditional vector field that we regress against, so to say, and for understanding then these things here, the denoising prediction and the noise prediction, which is supposed to correspond to like X1 prediction and to sort of delta, delta prediction maybe. Yeah, what do we have to look at?
So like in equation 24, I think if you didn't take the unconditional version, so if you like look at the derivation of, you don't actually have to look at it, but if you did look at the derivation of equation 24, their first stage is to like actually derive the conditional u, and then instead of this probability distribution p, they have this like another delta function. So what the conditional u looks like is like point towards say the place you're trying to go, like x1, by using like this delta function where if you're going to go towards x1, then you have mass or you have flow there, but if you don't, then there's zero. And then when you take the unconditional version, so when you move from looking at conditional probability paths to unconditional probability paths, and therefore like unconditional u's, then that's when you take an expectation with respect to
Okay.
distribution over x1, and that's where this probability over x1 is coming from.
Okay, so if we do our training, what is the vector field I should be looking at?
So when you do training, I don't think they actually need to look at the vector field, because what they do is they look at that the unknown quantity in the unconditional u is just this p1 given t xi given z. So like some clean data given noisy data, and then they just train that using cross entropy, I think.
So here, right, maybe we can look at this distinction. It is either this thing right here, or this thing is the unknown quantity. And this is what our neural network spit out. Is that right?
Yeah, so like the first one is if you're trying to like go towards clean data, then you need this x1 predictor. And if you're trying to go the other way towards your p0 source distribution, then you need the like noise predictor.
Okay, and will we be training with both of them?
I don't think they do. I think they only train one of them, but yeah, I'm not sure.
Okay, and if we only have the denoiser predictor, then is it, can I also sample backward in time?
I'm just trying to think if you can just like make it negative. I'm not sure if you can. I'd have to think about it more.
Yeah. All right. Then I think, right, so this guy takes in our a noisy thing, our noisy sample, and then our neural network is supposed to predict the clean position here, all the probabilities for the clean position. Is that right?
Mm-hmm.
and then we subtract, then we make negative. Yeah, it's kind of weird, I think, right? Because then during
You
sum,
can think of the delta function as like handling the fact that you needed to sum over to 0.
yeah, as handling the fact that we needed to sum up to 0. But why do we need to sum up to 0? That's only because for our sampling we have this guy right here, right? So can't we just won't this guy here just cancel out with this guy here?
Yeah, I mean, and then when you actually do the sampling, what it looks like is just you have some small probability of changing the token value, and that is like this kappa coefficient multiplied by p of 1. And that's like the actual probabilities that you use. And if you sum over all of those probabilities, you get 1 minus the probability of just staying still, and that they've just like rolled everything into one equation.
Yeah. Okay. So then also right during sampling, or right now during training, what do we do? Should we look at another part for discussing the training, or should we go, yeah, won't that?
Yeah, I mean, the training part is just like pretty short. It's just saying that you train using
here. Yeah. So we can say that we train with cross entropy, right? We sample this, or what's going on here? We have the noisy xt, which we sampled from the probability path that you defined however you like, and then you predict the. Okay, why do we have these multiple denoisers or these multiple W's here?
Yeah, so I guess this is where they're having this like one objective that trains both the X1 prediction and the X0 prediction.
Okay. So it doesn't just train the X1 and the X0 prediction, but it trains, right? We basically train it to predict all of the, let's go back to our probability path. Oh God, who did this this thing here? Yeah, we have this probability path here. This guy, equation 10. And we have our prior, our target, no, our prior distribution. We have our target distribution, and then you have the whatever you want in the middle, and you have these kappas, right, that interpolate between the stuff. And now during training, you just predict all these probability distributions, and yeah, I guess that's it.
Yeah, it's like you need to convert the unconditional form, like because your U vector is made up of these W's, you need to convert each W into the unconditional one by doing that training.
We need to convert each W to the unconditional one during training. Is that right?
Just having a look at the form for U.
Should I scroll somewhere?
Pardon?
Should I scroll somewhere? The form for
equation 21.
21.
So like the thing we need is the unconditional version of U, and you get that via equation 22, which is like W hats, and each W hat is like this kind of have some predictor over clean data and prior noise, and you use that to convert the conditional W into the unconditional W hat. So then you need to train each of those. You need to somehow obtain those W hats.
But isn't it like we can predict the W hats by just training on the conditional, or like the output of our neural network. Sure, it is the unconditional W, so these W hats, but we can obtain them by training with the conditional W's.
I'm just trying to think exactly what they do for training. Log W hat.
Do I scroll somewhere?
I'm just looking at equation 28.
Okay.
Yeah, because it's like in the forms of the equations that they actually use in the experiments, then they have this form of L where it's like on the last line of the paragraph where it's just training some predictor over x1 given xt. So I'm just like, in the case you have like 3 W's, I'm not exactly sure what this training objective is doing.
I think we just write in our, if we have our x0 and our x1, then most of the time the probability distributions, so to say, that we have for x0 and x1, and that we tell our neural network to predict. And right now we have 2 neural networks, right? One that predicts the x0, like the denoiser x1 probability distribution, and one that predicts the noiser x0 probability distribution. And then we just have the one hot vector, and our one neural network takes xt as input and is supposed to predict this x1, this one hot vector, and gets cross entropy loss. Then the other neural network, and the cross entropy loss is just the KL divergence to a one hot distribution. And then the other neural network, it gets as input also the xt and is supervised with the KL divergence to the other one hot vector, the one hot vector that corresponds to our x0. And now in the middle, we just have our W, which maybe is a uniform. And then do we just tell it to always predict the uniform distribution?
So y is sampled, y is sampled from the W itself. So if W was just a uniform, then the training target would always be uniform, just a random sample.
Yeah, this would be a little weird, right?
But I guess when you have this equation making W hat, you're taking the expectation with respect to P of x0, x1. And if the W is independent of x0, x1, then that just like marginalizes out. And then maybe it's actually like independent of the network parameters.
Yeah. So that would be the case for what we just said, right? The prediction of this uniform is always independent of the network parameters.
Yeah. So I'm not sure why you would ever need the loss to have more than 2 terms, like the x0 prediction and the x1 prediction. I don't know, like there are other W's that it would actually make sense to have this type of loss.
Yeah, but so maybe probably there are some other W's, or maybe they but in any case, we can train with only if we train also only with those two, we know that we can have these interpolations in the middle and like basically change our conditional probability path and cover more of the simplex, not really the simplex, but more of the space of possible corruptions. And I guess that's also sort of what you already have in your paper, right? That we can cover more of the space of possible corruptions.
I guess I think it's slightly different things. So we were like focusing on the corrector steps, or like this extra stochasticity, which I think is they have like a separate section where they discuss that.
Okay. Should we get to that, or should we maybe first make a look at results?
Yeah, we can look at results, and then I mean I think the corrector steps help, so then maybe we could go back.
Okay. Then can you explain what's this experiment?
Is generative perplexity the one where they use the language model? Yeah, I think, yeah, so then I think at the top is the language model they're using to assign scores to the generated pieces of text. I think this is on open web text. So I guess they train the model on open web text, generate a bunch of samples, and then use, say, like Llama 2 to.
So
Yeah.
Am I getting it right where we take Llama 2 and then Llama 2 assigns some likelihoods or negative likelihoods or whatever, or perplexity. We look at the perplexity of Llama 2. So we give it the sequence that we draw from our data, and then we look at how surprised is Llama 2 by the data, by this sequence, and we see this is a pretty good perplexity. It's not very surprised. So it's the loss, also the negative, or it's the best that we could get is 7 with this evaluation. If we have 7, then we basically would have natural data. Yeah, and then we look at what these models here get. So we use a language model that is much larger and much more expressive than the stuff that we're training here to evaluate the things that we're training here. Is that right?
Yeah.
Okay, and then I guess we see number of steps. Also, why are the sequences always of length 1024? Do you know that?
I guess that's the baseline they were using.
No, but I mean this text. Why do we always have text of size 1024?
I mean, isn't that just a hyperparameter that you would pick, like how you want to chunk the text?
But then I don't understand why the autoregressive would always have the same number of function evaluations.
Well, I guess you want to compare the same generative perplexity numbers, so you need to make sure that the length of sequence that the autoregressive transform is generating is always the same as.
So we cut off after 1024.
Yeah, I think you don't wait until it makes an end of sequence token. You just stop.
I see. Okay. Anyway, then we look at some numbers, and probably they use like the same neural network for all of these experiments, and we see, yeah, that your model is kind of good at this stuff, but their model is kind of better, a little better at this stuff. So where does the difference come from in this concrete training setup? Do you know?
I think so they're using a different schedule. So I think whenever they use our method, they use the linear schedule between prior and data, but then they use this like kappa T, and then they try a bunch of different schedules and find the one that works the best.
So you're saying we always use, actually, we stick with using this guy here. So we use this, but for you, the kappa, it would always be between 0, like it would be a linear interpolation.
Yeah, kappa T is just T when we were like introducing the stuff.
And for them, they now mess around with different schedules for the kappa T.
Yeah.
And that's the reason why we get the improvement from here, this line to this line. Also, very interesting to look at, right? Maybe some people have heard of score entropy discrete diffusion, which is this guy, I think. And yeah, these numbers are also pretty good compared to the other discrete stuff that we looked at before. And yeah, I guess they're kind of the same as your the numbers that you get. just now we can mess around with the schedule of your method a little bit and we get some better numbers. Let's look at the next one. Let's go through them quickly. So what are we doing different here?
I think this is where they're doing the conditional. So like they use this non-independent coupling where they have some of the data tokens in the prior sample. So then they can do like prompted generation, I guess.
Okay. Makes sense to me. Yeah, then
Oh, I just remembered. I think they're using the corrector steps as well in the previous table, which probably also helps.
the corrector steps. What are the corrector steps? So are you here using the corrector steps?
I don't think they included the correctors in that baseline.
Okay, but they included here.
I think so.
Okay, then what are these corrector steps and where should we look?
If you scroll up a few pages. This one.
Sampling backward in time?
A bit below.
Oh, sorry.
Yeah, so they have equation 26.
Mining the forward time and backward time. I see. Now do we use the backward time predictor for well, what's your explanation of what's happening here?
So to go from noise to data, you need to be using a U that if you were to like put it into the continuity equation, you would end up with a dtpt term. So like you're going through the right rate of change of your marginals and then end up with the data one. But like if you use the forward U, then you obtain a dtpt, like a plus dtpt, and you would, if you just that alone, you would get there. And if you use the backwards one, you get a negative dtpt because it's going the other way.
Yeah.
But if you add like 3 of the forwards and take off 2 of the backwards, then you still end up net with 1 positive dtpt. So you're still going on the same marginals towards data, but like because you're doing this like forward and backwards rate added together, you end up with like more switches during the simulation. So then you end up with like this like stochasticity.
Nice. Okay, so we train our forward predictor, right, and the backward predictor, and then we just go forward by a bit and we go back a little bit. We go forward by a bit, we go back by a little bit. That's what's happening here.
Yeah, pretty much. It's like you don't actually need to actually go forward and then back. You just add the 2 U's together and take one.
Okay. This seems weird to me that it actually helps, right? Because we still then end up with our single number. Now the number is just the combination of 2 neural network outputs, and the 2 neural network outputs were trained with different objectives. But yeah, maybe.
I think it like probably should note that like in the masking case that they actually use in the experiments, the backwards U is just like predicts mask because the noise distribution is just all mask. So you don't actually need to learn anything because it's always mask. So what doing this like forward and backwards does is just have some probability of demasking. And if you didn't use any corrector steps, you would only be demasking. But if you always also add in the other direction, then you also send some tokens back to being masks. And then so you have the like mask unmask process.
That's interesting. So that's also then kind of why probably inspiration for calling corrector, right? During training, we augment our space with the additional mask, like that we have the possibility of something being a mask. And then we have the noise predictor just predicts a probability distribution of something being a mask. And then we just have some probability of remasking the thing. And basically we find the positions that we are uncertain about and remask them.
It's not that intelligent. It doesn't actually like figure out which ones are uncertain. It just like randomly switches any of them.
No, I mean, we predict a probability for each position to be switched back to a mask, right?
But that, like the probability you predict is like P of X naught given XT, and X naught is always mask. So like P of X naught given XT is just delta on a mask.
Oh, okay. So this neural network isn't actually doing anything smart.
Yeah. Like for masking, you don't actually need two neural networks.
Right. So here we again only train a single neural network. And that's so unsatisfying. Ah,
I mean,
okay.
there's like some recent work where they're doing like more intelligent corrector steps that kind of have some nice looking at what needs to be fixed and then fixing them kind of process. But
Some recent work related to Sulin, or is this some other recent work?
I mean, maybe shoot. It was Shin that I saw was on the paper.
Okay, then maybe you can send it into the chat in a second while we look at the or I talk about the next set of results. Right, so now we have a question. I guess the issue is we don't have a good prior distribution for text other than all masks.
Yeah, that is a big issue.
Okay, but then let's quickly look at this other set of results. Right now, they write this autoregressive thing here, and for some reason, all the language model perplexities are kind of better in our all the language model based evaluations are our model does better. But in the HumanEval thing, what does this HumanEval thing mean? How does it work? Do you know?
No, I don't know. But I mean, autoregressive is still doing better, right? Because it's higher is better and it's getting bigger numbers.
Yeah, that's what I want to say. Up here in the language model evaluations, we're doing better, but in the down here, we're doing worse than the autoregressive models.
Oh yeah, I see what you mean now.
It's kind of interesting.
Yeah. What is the entropy? I mean, so they do have lower entropy for their the flow matching methods. And I found that like when you add these corrector steps, it can sometimes like lower the entropy of the generated samples, but also like focus more on modes. And so maybe you can like inflate generative perplexity at some cost of entropy.
But here, like we have 7.7, and right here the entropy is also lower, and it doesn't actually match up the oh yeah, it doesn't actually match up with the data entropy, right? Because Friends of the Sun in the audience, we basically should only look at the results where the entropy is like 7.7 here, the same as the data. Only then our results will be are actually good. Or like let's maybe look at only the numbers that are in the range 7.7, 7.8, and 7.6. So these here, for example. Right. So, but then still we can see a sizable improvement in the stuff that they mess around with, right? So we're looking at these numbers here.
Okay, yeah, they do look better in this experiment.
Well, but then again, we should maybe be looking at the best numbers, and then we want to be comparing these numbers up here with the numbers at the bottom, right? And then actually it turns out that Z looks the best in all of these experiments.
Yeah, I think when you have like the 1,000 NFE, it seems they do a bit better on the generative perplexity.
Yeah, so then if we look at it this way, then like we look at all the valid results in this table, so to say, where we don't have these crummy entropies here, then the best looks set, and then your method, and then their method, right?
New narrative.
No, I mean, yeah,
Yeah,
I
I
mean,
know what you mean. I can see what you mean.
right. So basically, guys, right, what is this entropy telling us? For example, if I throw my like I take progen2, like some protein language model, and I wanted to generate a sequence. Oh no, let's not talk about protein now. Let's talk stick with text. We have some language model, and it produces just and then maybe has a very low perplexity, and this yeah has very high likelihood under these language models if we evaluate with the language models. But the entropy of the the entropy of the sentence is very low, and it of course the sentence is also bad and not similar to what you have in natural data, right? If you just have a string of and repeated forever. Yeah, so that's why we really need this entropy here to be similar to what we have in the data. But I mean, I don't have a grasp on the magnitude to which we need it to be similar. Like, is 7.2 really unacceptable? I don't know. But if we assume that only like 7.6 and 7.8 are fine, and we make the narrative very good or very bad for this paper here, and ignore these other these three numbers that don't meet this quality threshold, then yeah, it turns out that what looks the best here is Z, and then the Andrew flow matching, and then their numbers. Anyway, maybe not too important to paint a picture like this. What else should we talk about? Yeah, this HumanEval. Does anyone in the chat know how the HumanEval stuff works? Like it seems to me that it's not actually a human evaluation, and it's just some evaluation that this Chen et al. People came up with, and that we throw that we test here then as well. Yeah, but turns out in this evaluation, the autoregressive model does better. Okay. Oh, oracle length. Do you want to talk about that? Do you know what the oracle length means? This almost sounds to me like we have a yeah an option for the flow matching model to predict a stop token.
When it's so the oracle length evaluates the performance when conditioning on the length of the solution. This is done by inserting an end of text token in the same position of the ground truth solution. So I guess they have to condition on something in this code task, and I guess they can condition on like they have this like whole sequence, and they put like a stop token, so it tells you like, oh, at this amount of the like available space should be used for the solution.
Yeah. Okay. Evaluation against prior blah blah blob image generation. I mean, I don't want to look at image generation now. Yeah. Anything else that we should talk about before we draw some conclusions and maybe look at the chat closer again? What do you think?
I think it would be cool to explore more of the like possible probability paths and not just use masking, because that seems to be the story in both like our paper and this one. Is like you have this the framework that can handle all these like general probability paths, but the one you end up using is masking, and then you just like maybe like as fancy as you get is like unmasking something.
Okay, then let's say we have someone in the chat who wants to do that. Can you say more concretely what they should do? Like, what is the probability path that we should try out?
I think it'd be cool to have some probability path that like uses the like continuous diffusion idea that on images you have the like high frequency content and the low frequency content, and then you start generating the like low frequency stuff, and then you like refine the details. And like maybe there's some kind of analogy of like high frequency, low frequency text content, and then you would have some probability path that like first destroys high frequency text. And,
Yeah.
you know, I don't know what that would look like. I think it probably isn't independent on each token, because all probability paths are like independent corruption processes. But I think if you actually want to like do like high frequency, low frequency stuff, then you need some kind of process that can like take everything into account.
Yeah, maybe that would then have to be learned if we don't understand what's going on, or if we have some other data modality than text, because for text I can hardly imagine it, but if we have some other data modality than text, then maybe we can tell where the high information content and low information content parts are. So maybe that's actually the case, for example, for regulatory DNA, that we can tell which part of the sequence carries information and which part doesn't. Or at least maybe it would be very easy to learn for DNA as well. And then exploring something like this could work very well for regulatory DNA. Yeah, that sounds plausible to me.
So I have an example maybe for the protein space, or maybe
Yeah.
also in DNA. I mean, you've got Blossom matrices which describe the probability of transitioning from one amino acid to another amino acid in families of different protein sequences.
And when you say
People would-
that describe the probability of transitioning, you mean the probability of transitioning in evolution, right?
Yeah,
how
exactly.
often we count how often does a transition happen in evolution, and then we put this into this matrix.
I mean,
Yeah.
yeah, like given that this amino acid has changed, it tells you the probability of transitioning from one amino acid to another amino acid. And those are calculated from very large families of.
Is that like the Blossom matrix?
Yeah,
Yeah.
that's what I'm describing.
Yeah, I think someone has tried using that. I can't remember if it was.
There's a paper in the discrete diffusion for inverse folding space. It's called grade IF or grad if, this discrete diffusion model, grad, something written like this. And they use this for discrete diffusion, but should like to define their noising process. But is this now like, does this really tell us what part of the sequence is high information content and what part is low information content? I mean, everything is still, all positions are still being treated independently from each other. I think this is not quite what would be happening, right?
In that case, you might have to look at conservation in protein families. And then you could try and define you could try and define a process that moves around that protein family.
You have your sequence, you get an MSA, and then the MSA tells you like sort of which part is more conserved, which part is less conserved, and then the more conserved part is the more information rich part.
Exactly. And you also have pairs of positions that are conserved, right? Those might be your contact points.
Yeah.
Then you'll get higher order like triples and higher order tuples of pairs that are conserved as well.
Yeah. What do you think about that, Andrew? Like, if we have you know what MSAs are, right, and so on. What do you think about defining highly conserved, not conserved with that?
Yeah, I'm thinking something like that, where you want to be able to somehow like so like with the protein families, you have like the as you're going through the corruption process, your sequence is like narrowing down which protein family it could belong to. So like it starts with like everything, all protein families being possible, and then that's like the equivalent of like averaging over every image. And then as you like start de-blurring, you start like narrowing down which like superfamily and family
Yeah.
that you belong to. So would that mean that you first corrupt the non-conserved? So then you're like moving around a little bit into all the protein sequences that are common to this family. And then there's like these core regions that are common that you don't corrupt until later on when you start moving to like the higher spaces.
I mean,
Wait.
protein sequences have these concepts of domains, right? And domains are typically regions that perform the same function. But then within that domain, you might have only a few positions, like the catalytic.
Yeah, but Andrew was now
density.
asking if we have this domain, and we maybe know this domain is more conserved, or we have this other catalytic site which is now more conserved. Then do we want to first noise the catalytic site, or do we want to first noise the less conserved regions? And I think, yeah. So Andrew, what was the point that you were making for high frequency?
I was trying to think of corrupting the non-conserved first, because I feel like that would be the high frequency detail that's like you know mostly what the function is, but like there's just these like specific little regions that don't actually influence much, but they're just like this like high frequency detail, and then you corrupt those, but then you still basically know what protein's doing because you've kept the conserved domain. Then you maybe corrupt them a bit so that you know in general like maybe it has this function, but you don't know specifically what the domain is.
Yeah. So first we want to add noise to the high frequency areas, / we want to add noise to the unconserved areas.
That's my guess.
Then go ahead and try it, friend of the sun. Yeah, maybe that's a nice thing. But then that's kind of interesting. Let's maybe also look at the chat a little bit. Is it possible to give a simple explanation on how to sample in the simplest case, given a denoiser network trained with cross entropy loss? Let's first check if Radev is still in the chat. Radev, yes, he is still here. So a simple example. Right, we trained our neural network with cross entropy loss. Now we have our fully noised sequence, which are all masks. You throw all the masks into your denoiser, into your neural network, then your neural network predicts you these numbers that add up to 0. Then you take the numbers that add up to 0, right? That have the and the amount of numbers is the size of your vocabulary. So maybe 50,000 if we're talking about words or something like that. And then these numbers that you have for each, like Andrew, correct me anywhere that I'm wrong, right? So do I have like these 50,000 numbers for every position that I predict?
I think so, but I think if you're doing cross entropy, you're probably not using the U. You're probably just directly doing cross entropy on this P of x1 given xt. So that will be you're outputting a vector that's like softmax the logits, and then you maximize the log probability of the correct token.
Yeah, that's fine, right? And fits into what Radi was asking about. And then we have this prediction. We multiply our prediction with a little h, with a little delta h, which is the corresponds or is 1 over the number of denoising time steps that we want to have. So this is our little h. Then we add it to the one hot vector that corresponds to staying the same, like leaving our token the same. And then we have this new probability vector here. And the new probability vector we we sample from.
Yeah, when you're doing the Euler sampling. I just think in training maybe they don't actually materialize you.
Yeah. And I guess during sampling in what we just explained, you also don't need to materialize U, right? Because you don't need to do the subtraction of the delta.
Yeah, I mean, it gets into like the details of how exactly you want to implement the Euler sampling, but you don't really need to.
So I guess you literally just have a neural network that predicts the probability vector. Yeah, you literally predict a probability vector and not the vector that adds up to 0. And then I guess that's where the confusion came from. Sorry, my bad. You literally predict a probability vector while training with cross entropy, and then you sample from that during inference. Yeah, like saying it this way sounds very boring, right? And I guess that's what all these methods do. And the only thing that they change is what is the input to the neural network? Like, what is the probability path? And now here in this paper, we mess around a little bit with the probability path. So it seems like there's not much. Yeah, there's really not much going on here in the end.
Yeah, I mean, I think when you're just using the mask process, I think we're maxing out performance that you can squeeze from like a process that masks and then uncorrupts them in a random ordering. So I think like these maybe like more informed corruption processes, more informed correctors might be, I think it's difficult because like for the past few years, mask has always been better than anything else.
Yeah,
It
but
seems
now
do better.
like Radif is saying, okay, wow, that's simple. But I kind of want to point out, right, this is also already what we did in Andrew flow matching. Like this is not just something that's happening here. Yeah. But now maybe we have it like generalized a little bit nicer, and like the interpolating between like going from one distribution to the other, and then like going between two data distributions is formalized nicely here.
You do like coupled distributions.
Yeah. So I think the paper here is interesting to look at, and yeah, well worth. And if someone wants to learn about discrete flow matching, then yeah, maybe they can start with this one instead of with yours, because it's sort of, but I think the setup here is also maybe almost too general for giving a simple understanding. So maybe reading your paper is simpler. But then there's also all the protein shit in your paper, so maybe that's a bad thing.
We did try and like simplify it by having like the linear interpolation and stuff.
Yeah.
But I mean there are parts in our paper that are general as well. So like I mean maybe read both.
Yeah, but that's more work. Maybe that's but anyway, I think it's now probably right. I will continue calling this Andrew flow matching. And I think this is like you sort of now came up with the definitive discrete flow matching framework, and that must feel kind of good, no?
Yeah, I mean it's good that like Meta took it and scaled it up and seems to work well. So it's exciting.
Yeah. Well, we should also talk with the authors of this paper here, what they think about it at some point. Anyway, then I'm making many contentious statements that are on the border of probably not correct and very subjective. So let's get back to some more objective statements, which are, for example, I think this paper is well worth a read. And yeah, let's think more about what can we have in terms of probability paths that are more than just interpolating to something masked. That's my last word. Andrew, what is your last word before we call it a day?
I don't know. I think it was a good last word.
Okay, that's good. Then thanks for joining Friends of the Sun. See you guys next week. And